Okay. Now we move on that suppose the process is adiabatic. We have seen the isobaric process, that is the constant pressure process, constant volume process, isochoric process. Now let us see that if the process is adiabatic, that is del q is equal to 0, then what happens? Applying the first law of thermodynamics, utilizing this, del q is equal to du plus p dv. If dq is equal to 0, we can essentially bring down this equation as du is equal to minus p dv. Similarly, suppose if h, that is the heat function or enthalpy, can be written as u plus pv, and if we take the differential, dh is equal to du plus pdv plus vdp. However, du is equal to minus p dv. Therefore, we are left with dh is equal to vdp. That means, for an adiabatic process, du is equal to minus p dv and dh is equal to vdp. Moving further, for a thermally perfect gas, the internal energy, please note that for the thermally perfect gas, the internal energy and enthalpy both are only the function of temperature. That is, we have started with a general case u taking as T and P and H T, and the H is also T n, u started with u T n V and H T n P, and we brought out that du is equal to C V dt and dH is equal to C P dt. Now, if we talk about thermally perfect gas, then the thermally perfect gas, the both internal energy and enthalpy are only dependent upon temperature, not on the volume, not on the pressure. In such a situation, if we rewrite this equation again, what we find that u is equal to function of T and V, then since this is only function of temperature, therefore, rewriting this thing, we can obtain directly that du is equal to C V dt. And similarly, the H T and P, and now since it is only function of temperature, we can bring down this directly as dH is equal to C P dt. Why that is so? Earlier case was a general case where we have seen that both u and h, which are dependent upon two variables, were leading to these two equations, whereas they were coming through when the process is isochoric in the first case and in the second case, that is isobaric case. However, when the gas itself is a perfect gas, that means their both internal energy and enthalpy are dependent only on temperature, then also we find the similar expression, that is of internal energy as well as enthalpy. Therefore, we can essentially say that both expression du is equal to C V dt and dH is equal to C P dt are universally valid as long as the gas is perfect. Now, let us further see that this relationship which we are going to talk about, Mayer's relation, already we have seen from macroscopic point of view. Now, since the equation of state is equal to P is equal to PV equal to RT, if you differentiate, then we can say P dV plus V dP is equal to R dt, and again using the heat function and differentiating, dH is equal to du plus P dV plus V dP, and if we shift du from here to this side, left hand side, what we remain with is this, and using this from the equation of state, we can directly write down R dt. Further, since as long as the gas is perfect, we just said that dH is always C P dt and du can be written as C V dt, hence it brings to again the equation which is known as Mayer's relation, already seen in the kinetic theory of gases talk. Now, a calorically perfect gas in our case is that which obeys the calorical equation of state. In our case, since Cp and Cv both are defined in terms of in terms of internal energy as well as temperature. That is, it relates this Cp and Cv equation relates the enthalpy as well as internal energy with respect to the thermodynamic property, thermal property T. Hence, a gas which obeys such that its thermodynamic, its chemical property Cp is not a function of temperature, and also the Cv is not a function of temperature, and they are constant. In turn, Cp and Cv ratio, that is gamma, is also constant. We say this gas obeys the calorical equation, and hence it is calorically perfect. A perfect gas in total therefore defines as the gas which is both thermally as well as calorically perfect. That means it obeys the equation of state as well as its Cp and Cv are not function of temperature, and they are essentially constant. That last point, one important, which we can see here, a gas which a perfect gas is which is both thermally as well as calorically perfect. However, please note, if a gas is said to be calorically perfect, it implies that automatically it is thermally perfect, but the vice versa is not true. That means, if the gas is thermally perfect, it cannot be said that it is also calorically perfect. Now, we will talk about the limitation of our fluid, that is air, with respect to the temperature. What happens? The air, as I said, that it is assumed as the diatomic gas, hence the specific heat is taken as 1.4. Now, when the temperature of air in a process is less than 500 Kelvin, it is said that it is both thermally and calorically perfect. That means, it follows the equation of state as well as its Cp is equal to constant and Cv is equal to constant. In turn, the ratio is also a constant. However, when the temperature is in the range of 500 to 2000 Kelvin, the air is still thermally perfect, that in this range it obeys the equation of state P equal to rho RT. This, however, its Cp and Cv both becomes the function of temperature. That is, in this range 500 to 2000 Kelvin, the air is calorically imperfect. However, interestingly, it has been found that even though both Cp and Cv are function of temperature, in this temperature range, the gamma still comes out to be constant. However, when we move ahead or increase the temperature beyond 2000 Kelvin, and in this range 2000 to 4000 Kelvin, what happens? The oxygen present in the air start dissociating, such as like this, and it start giving the free electrons and the 2 oxygen ions. Now, in this case, the gas is no more thermally perfect, and it becomes thermally imperfect, and it is also calorically imperfect. Temperature as high as 4000 Kelvin. If we move ahead, then nitrogen in this temperature range, the nitrogen start dissociating, which start dissociating at 4000 Kelvin and completes around 9000 Kelvin according to this relationship, and this is again fetching in the flow the free electrons. Please note, these free electrons forms the cloud, and during the process, like such as space shuttle re-entry, this is termed as blackout phase. Hope my friends remember that this was the phase during which the Columbia space shuttle in 1st February 2003 is crashed totally, and we lost the famous scientist named Dr. Kalpana Chawla of India. Now, you can see this thing, this is the space blackout phase, when it occurs that when the space shuttle used to enter at very high Mach numbers, something around Mach 28 to 32, on an average Mach number 30, when it tried to intrude the atmosphere, it comes into atmosphere, approximately the altitude at 65 to 70 kilometer above the sea level, the temperature generated in the region at the nose somewhere here is very high, and this high temperature essentially completely dissociates this nitrogen event. That means the temperature here, taking the dissociated effect into account, it is approximately 9200 Kelvin or so. Under this, a sufficient number of free electrons forming the electron cloud is present in this zone, which disrupt the signals from this cockpit of the space shuttle to the ground relay center. And it takes around 15 to 20 minutes in which the ground control unit does not have the information of space shuttle, and that was essentially happened with the Columbia space shuttle. Now, we can see from the kinetic theory of gases, we have defined here, which symbol we have used here, there we essentially used alpha, and we have said that 1 plus 2 by alpha is nothing but a general gamma for polyatomic gases, where alpha is nothing but your degrees of freedom. For monatomic gases, where only 3 translational motions are possible and no rotational as well as vibrational, we brought out that if substituting this 3, then we brought out the gamma for monatomic gases as 1.67, and for diatomic gases such as air, 5 the alpha is turned out to be 5, that is 3 translational degrees of freedom and plus 2 rotational degrees of freedom, and hence the gamma turns out to be 1.4. Now, for polyatomic gases, this is something like more than a slightly greater than unity. Therefore, the gamma, which is a very narrow range parameter, is lying between 1 to 1.67. You have to remember this relationship, that gamma is a very narrow range parameter. Now, we will move towards in the case we will try to derive the equations which is undergoing, that is the system is undergoing the isentropic, that is the constant entropy processes. Let us see that from second law of thermodynamics, where we have written ds is equal to del q by t, which gives, we can be rewritten as del q is equal to t ds for reversible processes. So, assuming we are discussing the reversible process only, and then the first law of thermodynamics gives here, clubbing the first law and second law, we can right away say that T ds is equal to du plus p dv, and this can also be written if we take into account h is equal to u plus pv, then we can write down the another form T ds is equal to dh minus v dp. Now, for thermally perfect gas, we know that dH is equal to Cp dt. Then, substituting this value here, we obtain ds is equal to Cp dt by T minus V by T dP. However, from the PV equal to RT, that is the ideal gas law or equation of state for a perfect gas, we can write down straight away ds is equal to Cp dt by T minus R by P dP, and which can be solved if the integration is done both sides. Then let us say the change in entropy of the process is delta S, integral of ds is equal to Cp, and if the temperature is changed from T1 to T2 because the system is brought from state 1 to state 2, then let us say if the pressure is changing from P1 to P2, then doing the integration dt by T will become ln T, and the logarithmic T, and this becomes ln P, that is logarithmic P, and hence substituting the limits, we can get delta S is equal to Cp ln T2 by T1 minus R ln P2 by P1. This is the first relationship of entropy change for a perfect gas. Now, moving ahead, if we take the Cu is equal to du is equal to Cv dt, and we use the original expression of du plus Pdv, then we can write down delta S is equal to Cv ln T2 by T1 plus R ln V2 by V1, where V2 and V1 are the volume, specific volumes. And then if the process is isentropic, in this case, what we obtain here, that if the process is 0, the entropy change is 0, we can see here Cp ln T2 by T1 minus R ln P2 by P1, because the first case we are considering here, that if we are putting here it is 0, then we can write down Cp ln T2 by T1 minus R ln P2 by P1 is equal to 0. Now, taking this equation, we can get here something like this, that is ln P2 by P1 becomes Cp by R ln T2 by T1, and since Cp and Cv ratio, that is gamma, is equal to Cp by Cv, and then using Cp minus Cv is equal to R, that is the Mayer's relation, we can straight away see that Cp can be written as gamma R upon gamma minus 1, and Cv can be written as R upon gamma minus 1. Using this here, P2 by P1 can be written as T2 by T1 to the power Cp by R, which is nothing but this, and hence we can finally write down the P2 by P1 and T2 by T1 expression as gamma minus 1 upon gamma. Now, considering the doing the same exercise with the another equation of entropy change, we will obtain Cv ln T2 by T1 plus R ln V2 by V1, that is in these terms of specific volume. Doing the similar exercise, we can bring down the equation something like V2 by V1 is equal to T2 by T1 minus Cv by R, where Cv is equal to R by gamma minus 1, and hence this expression is obtained V2 by V1 is equal to T2 by T1 to the power minus 1 by gamma minus 1. However, since rho is equal to 1 by V, and hence rho 2 by rho 1 can be written as V1 by V2, that is replacing V2 by V1, we can replace it with rho 1 by rho 2. Doing so, we can write down immediately that rho 2 by rho 1 is equal to T2 by T1 to the power gamma 1 upon gamma minus 1, and hence the relationship between the pressure, the static pressure change, static density, and then static temperature is something like P2 by P1 is equal to rho 2 by rho 1 to the power gamma is equal to T2 by T1 to the power gamma upon gamma minus 1. This is termed as famous isentropic relations. Now, from the energy equation which we have derived for an adiabatic flow, we have seen that H naught is equal to H plus V square by 2. Now, for a perfect gas, we know that dH is equal to Cp dt. However, if the gas is perfect, if dH is equal to Cp dt, if we integrate both sides, then also we get Cp dt. So, from 0 to H and from T is equal to 0 to T, we again can say that H is equal to minus, let us say if this H naught, H minus H naught is equal to Cp T minus 0, and we have given the argument that at t equal to 0, the H naught is taken as arbitrarily 0, and hence H is equal to again Cpt can be written. That means they are differential as well as the quantities like H, Cp and T, H is equal to Cpt is also valid for a perfect gas. Using so, for a static enthalpy case Cpt, and for stagnation enthalpy we have seen we have written like H naught equal to Cpt naught. Substituting back in the energy equation, we will obtain something like this: T naught by T 1 plus V square upon 2 Cpt. However, replacing Cp again with gamma R upon gamma minus 1, we can write down T naught by T is equal to 1 plus V square multiplied by gamma minus 1 upon 2 gamma RT. This expression, that is gamma R T is written as a square, or a is equal to square root of gamma r t is the expression for speed of sound in compressible flows. That means, if we do this thing, then T naught by T is equal to 1 plus V square by 2 gamma minus 1 upon A square, and since V square, we can see here that V square upon 2 A square into gamma minus 1, this V by A will give you m square, and hence we will bring down the equation as T naught by T is equal to 1 plus gamma minus 1 by 2 m square, and using the isentropic relation in, that is, we have just derived it here this relationship, then we can represent in the both stagnation state and static state, stagnation temperature state, static state, the relationship something like that, P naught by P 1 plus gamma minus 1 by 2 m square to the power gamma upon gamma minus 1, and rho naught by rho 1 plus gamma minus 1 by 2 m square to the power 1 by gamma minus 1. And hence, further if we see that for a adiabatic case, that is adiabatic perfect case gas, T naught essentially in the state change is constant. In doing so, if we bring down if we consider the relationship of enthalpy change of the temperature and pressure is like this, using the previous this expression, that means Cp ln T2 by T1 minus R ln P2 by P1. If we are considering that the state change from a stagnation state from state 1 to stagnation state 2 in such a sense that the process is carried out adiabatically, then writing delta S and denoting S stagnation state 2 minus S stagnation state 1 as Cp ln TO2 ln TO1 minus R ln PO2 divided by PO1, and since the stagnation temperatures are constant, therefore, this term is 0. Therefore, whatever we left with SO2 minus SO1 is equal to minus R ln PO2 divided by PO1, and since minus sign if we are taking inside, it will be reversed, and hence we are left with this expression which is shown here. That means, SO2 stagnation state 2 minus S stagnation state 1 is equal to R ln PO1 by PO2. But please see here that since this expression does not depend upon velocity, that is why unlike enthalpy, there is nothing like stagnation or static enthalpy entropy. That means, the entropy does not depend upon the velocity, therefore, there is a single entropy, and we cannot distinguish like static entropy or stagnant entropy, both are essentially same. Okay. Now, in the compressible flow design, suppose during the experiments you have the model and you have to propose the experimental data from the experimental data how and utilize to or design to a prototype. Let us say you have, for example, if we have the aircraft model and we have to perform the wind tunnel testing and we have to correlate the obtained data to its actual aeroplane, then we call this smaller aircraft as a model and that aircraft as a prototype. In this circumstances, assume that the both model as well as the prototype are geometrically similar. Under this condition, if the flow pattern are similar, considering all the physical equation governing equations, that is continuity equation, momentum equation, energy and equation of state. That means, For similarity between model and prototype, we know from our fluid mechanics background that they should be geometrically similar, kinematically similar and dynamically similar. Geometrically similar is that the both model and prototype should be having the geometry same, that is at the same point under consideration the length scale should be in a particular proportion. Further, at all point this geometric scale should be constant. Kinematically similar, that is, except the forces, the flow pattern over both model and prototype should be similar. Dynamically similar means that the forces acting when the flow passed a model or a flow past a prototype, they also maintain a constant behavior. That is, the ratio of the forces in both model and prototype are having a constant. In doing this exercise in compressible flow regime, the 4 particular non-dimensional parameters are obtained. The first parameter is the Mach number, which is written here, that V by A is essentially brought down by non-dimensional analysis of inertial force to elastic forces. Similarly, if doing so inertial forces to viscous forces analysis, non-dimensional form will lead to Reynolds number of rho VL by mu. Moreover, the specific heat ratio gamma is equal to Cp by Cv, and further there is additional number that is called as PR. PR is equal to mu Cp by kappa, that is the Boltzmann constant here, and I am sorry, this is the thermal conductivity, viscosity and Cp is the specific heat at constant pressure, and because the heat transfer is also accounted in the analysis. Now, since any flow model, that is a model like aircraft or a spacecraft, is kept under the flow situation, then a boundary layer will always grow over the surface of the aircraft or spacecraft. That means there are 2 regions, a inviscid region outside the boundary layer, this, and inside the boundary layer, the viscous effect. In the outside region, which is also termed as potential region, the heat transfer effects are not that much important, and hence the gamma has a very weak influence. Therefore, in the outside potential region, the dominant parameter is m, and hence it is the only similarity parameter, while in the inside the boundary layer, the apart from Reynolds number, because this is a viscous region, both gamma as well as PR, that is the Prandtl number due to heat transfer, are also accounted, and they are also dominant parameter. Therefore, in the viscous region, m, Re, gamma as well as PR all are similarity parameter, unlike the potential region where Mach number is only the similarity parameter. Okay. Now, let us see the final thing, that what we have studied in the thermodynamics of compressible flows. What we said, that in the incompressible flow, the energy change is such that is taking place such that the energy change is very small, and we can even neglect that. Why it happens? Because in this scenario the heat content is much greater than the kinetic energy for an incompressible flow. That means, if whole kinetic energy is converted, then also the temperature of the system is not affected. That means, it be due to its larger heat capacity, and because of this, in doing so, even though whole kinetic energy is converted into the heat, even though the both static and stagnation temperature difference, or static property and stagnation property difference, are not much, that is, they are very small. So, we do not define static and stagnation properties differently in an incompressible flow, while in the compressible flow if the process is of taking place at very high speeds, then in this scenario, since the kinetic energy of the flow is much higher than heat content, therefore, a small change in kinetic energy leads to large change in temperature, and that essentially brings down the fact that both static and stagnation properties are different in a high speed flow, and that is why we define both static property and stagnation property, and they are considered. In turn, in a high speed flow regime, the final governing equations which deals the high speed flow are continuity, momentum, energy equation, that is also termed as first law of thermodynamics, second law of thermodynamics for the process to be carried out in whichever direction, and as well as the equation of state for a perfect gas. We can say P equal to rho RT should be taken into account and the analysis take place.